Welcome all of you. So this is our last session on this course, study guide in the organic retrosynthesis, a problem solving approach. And we have covered most of the concepts in this retrosynthesis. So just let me, we will wait for few more minutes to join more peoples and then we will start our session. Hello. Okay, so these are some just overview of our course that we have studied in from last 12 weeks. So mainly we have studied more focused on the synthesis and retrosynthesis part of these some simple organic molecules in terms of their retrosynthetic analysis, and we did several retrosynthesis of the several small molecules, and from few in between we have also more focused on some enantioselective synthesis, and obviously we have covered a few examples regarding this retrosynthesis which involve the asymmetric synthesis. And at the end of our this session, so this is our last session, so we're gonna see some actual examples of the retrosynthesis which in particularly which are actually published in some articles. So we'll see some examples based on that one. So before moving to these problems, I would like to open the session for any question answer. So we can discuss that question answer first, and then we'll move to the examples that I have taken for today's sessions. So please let me know if you have any doubt. We'll discuss that one. Or else, if you don't have any doubt, we can directly move to the actual problem that I have taken for today's discussion.
Yeah, you can go now. Actually, assignment 11, there is some problem. If it is already done, but I get some problem. I am not understanding why my answer is wrong. So if you explain
Okay.
these things, assignment 11.
Okay, I will go check that problem
Yeah, yeah,
actually.
yeah.
So,
I got wrong something. So I thinking that explanation will be better for me.
okay, so assignment 11 and the can you just if you so if you have any the question number, then you can tell me, or I will just
Roughly you can go. Yeah, which one? You can open it, then I can tell you which one
okay,
because
okay.
number
I
I
will
forgot.
better I will share entire screen.
Yeah, 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 yeah.
So can you have a look? Can you see the screen right now?
Yeah, I'm watching that one.
Okay, so the
First one is
first
okay.
uh,
It is okay. Second one, can you explain please?
okay, the second I will take this problem actually then.
The second one also probably third one, right one.
Okay.
Second one.
I will take all the problem first and then
Yeah,
we'll
I'm
discuss.
just
So
muting, otherwise it will
this
be problematic to listen. So I'm just mute it. So
okay.
you just explain, okay?
So the second one and anything else.
Second
So you
and down also there. There is 16. So few words I got wrong. This one also.
okay,
This one.
fifth
Yeah, yeah. This one.
and
Down to
just
down to.
so this okay. Um,
Is this okay? Yeah, that I got okay.
then the seventh problem is based on the oxidation or sorry, opening of this epoxide.
Yeah.
And then the eighth one. Okay,
This
so
one I need explanation once. And these two down. This is
okay,
the which number I'm watching. I can't see. This is my small.
okay.
I'm
I will
studying
take
in
the
mobile.
problem.
8, 9, 10. 8, 9, 10. You can go. Actually, mobile screen is very small at present.
Yeah, yeah. So I will try to take. Okay, yeah,
Yeah.
no worry. 10th. Okay, I will 8, 9, 10. Okay, I have taken all the screenshot of this question
Yeah.
and
Yeah.
just keeping it on the PowerPoint so we can discuss
Yes.
on
Yes.
the
Yes.
PowerPoint. Okay.
Okay.
Uh,
11 I got okay. Again 12.
Okay, the 12th one. Okay.
12. 12, 13. 12, 13. 12 and 13 and down, please. 14 is okay. 14 was okay. And 15, 16, I forgot what is the question. 14 was okay.
Okay.
Till if it will be better if you discuss about that. 14. Actually, I
Yeah,
did it. But yeah.
I have taken this one.
Uh,
So let's
uh,
see how it works. So we'll
yeah.
discuss all these
Yeah.
problems then.
Okay. Okay. Thank you. Thank you.
Okay, so these are the some problems. We'll just so I hope my screen is visible now. So these are the some problems based on the week 11 assignment, and let's discuss these one by one. So perfect. Right. The here the this question it mentioned. So I'll just zoom the question first. Actually, okay. Okay. So what will be the major product form in the sequence? Major product form in the reaction sequence. Okay. So what we have here? B2H6, right? So B2H6 and then the acid here. So what happened? We have here the ester group, and here it is acid group. And if you remember when I have discussed about the reducing reagent, so what I have mentioned in the reducing reagent, so if you have the any acid functionality, so BH3 uh, THF works quite perfectly. So this is also kind of B2H6 basically. So this is the sorry, not F, it's H, and this again the H3, right? So this is what about? So this is basically a BH3 source, right? And if you look at the reactivity of the BH3, it is shows more reactivity towards the acid than the ester. So acid are gonna get reduced to the corresponding alcohol, right? So what we get intermediate here? I will directly draw it down the intermediate. So we have this chiral center remain as it is. Now here, what we get? We get this CH2C double bond OH, right? And in this case, what we have? C double bond O Me, and here downward directing methyl group. Then what happened? In acidic condition, so basically this hydroxide group attacks on the ester, and OMe group get eliminated. So basically we get the cyclization product. So up to here is okay. So what we get here, the product here, we get the alcohol by attacking. So this alcohol basically I have just drawn directing this side, right? So this alcohol I just draw in this side. So if I just draw in the same manner, I will just so you can see here. So this is the alcohol I just drawn here. Now the question about the stereo centers, right? So if you look at the stereo center, so this stereo center is remain unaffected. So that will be as it is in the as it is in the product. Up to here, I hope it's okay. Now what about the stereo center of this methyl? So the final stereochemistry of this react center also should be remain unaffected. So if you look at the stereo center, the configuration, if you just do the RNA configuration in this, both of the react center, let's say I will do on this one, the methyl one. So I will just label it as a chiral center A and chiral center B. So this is our chiral center A. This is our chiral center B. And if I just give the RNS configuration at this chiral center, so if you look at here, so it will be the one, this should be the I just try to remove other unnecessary part. So this will be this entire group will be act as a second priority. So this was the first priority, and the methyl is third priority. And methyl is directing downward. Fourth priority group is directing upward. So what happen if you give the numbering 1, 2, 3? This looks clockwise, but it should not be R. It should be the S then, right? So the stereo center here, it has the configuration yes. So in the product also, if you look at the reaction is not gonna occur on this stereo center. So in the product also, the the configuration of this stereo center, it should be S, not R, right? It should not be changed. So if you look at the stereo center on the product, so what is here? So it will have the 1, 2, and the 3. So this will be S. So in this answer, the stereo center is preserved. So this is the one at this stereo center. It is okay. Now the question about you have confused between the A and B, right?
That's the things, A and B.
Yeah. Yeah,
How
okay.
the
So
stereo center change? Because we are not disturbing that stereo center, na?
yeah,
CO2
so
will meet outside the group.
it's not change actually. It's not the change. It's not change. If you look at here, if you just give the assignment, so it will be the 1, this will be the
Mm,
2, and this will be
mm,
3. So what it will
mm,
be? It will be, yes, fourth priority group is already directing downward. So we don't have to invert the stereo configuration,
mm.
right? So this is the
Okay, okay.
yes.
Acha,
So we have preserved the stereo center, and there is no issue with this the stereo center at this center, right? This stereo center is okay,
acha.
right? So which is again it is the constant, so no worry about that one.
Okay,
So
okay.
if you just do the assignment, so you can also approach the question in this manner also.
Probably I did
So
B, that's why
yeah,
I got wrong.
yeah. So it should not be. You have if you just look at here, it's directing downward, and here also direct downward. You can directly correlate in hurry directly. You can select this one, but if you look at closely, so the linking is different here. So if you just give the numbering straightforward 1, 2, 3. So if you do the numbering, it will be looks yes, but since the fourth priority group is directing upward, so you have to invert that one. So it will be the compression at this air center. In this option B is R. So it should not be our answer. So that's why the answer A is the correct one, right? So I hope you got the answer for this one. So here two concepts are main here. So the reactivity of these BH3 towards the acid is more compared to ester. You have to keep remember that one. And the second point, the stereo center, this chiral center is not taken part in the reaction, so they should be remain unaffected in the product. So that's what our option is. That's why the option A is the correct option. Okay, we'll move to the next question. I'll just zoom out this question. Okay, so this is what we have. The second question, in this one, which is the correct retrosynthetic pathway for the following molecule? So what we have here, this is our target molecule. And if you look closely, how the synthesis of the target molecule can be achieved. So you can clearly see from this one. So what are the groups that we have here? So basically, if you look one by one, so then we can easily understand. So here you can see this is one. Okay, so in first thing we need to identify the stereochemistry here, because looks like all possible answers are same, only difference in the stereochemistry, right? Then if you look closely at the stereochemistry, both these bonds are seen to each other, particularly this bond and this bond are seen to each other. So in the starting material also we have to think of only seen bonds, particularly this carbon oxygen and this carbon carbon bond. So this bond should be the seen to each other. So in this one these bonds are seen, and in this one also these are bonds are seen, in this one also these bonds are seen. Now what about uh, the reaction? So if you just do the synthesis of this one, what will happen? So in acidic condition, in this case, sorry, in the basic condition, this hydroxyl group in the first option give O negative, and it for the attack on this position, it give the product. So in which you can see we get should be the beta. This also should be the beta directing, and from this oxygen to this bond carbon. So this is the new bond form, right? So this is what product we get. If you look at the second option, in the second also what we get here. So it will be O negative initially because of base, and then it attacks on this position on the back side. Sorry, on also on this side, and this will be OTS will be eliminated. So in this case, what happen? What product we get? So we get basically. So this is O. So I will just separate these two from each other options. Okay, so what product we get here? We get, so this stereochemistry remain unaffected O. This stereochemistry also remain unaffected, and this bond will be formed. So this is what we get. In the third option, what we get here? In the third, both are seen. So OH. So this will be O negative then in presence of base. And if it attack on this carbon, it should be attack from backside, and then it will be OTS eliminated. So what product we get here? We get some different product here. So here we get here CH2. This is O, and it is attack here, right? So what this is what we get in this case. And the so in this case, remember the attack should be takes place from the backside. So this will be here. Then what we have the fourth option. So we have OH O negative. So that O negative attacks on again here from the backside. This will be eliminated. So in this case, if you look at this OTS, it will be eliminated, and we get here OCH2, and this should be remain as it is. So any doubt in the product that I have mentioned here? So this is the first product, this is the second product, this is the third product, and this is the fourth product from these three actions. So why I have drawn the stereochemistry in some case like this. So in this particular, let's say directing like this, and this one directing downward, and in this also, sorry, in this I should, uh, okay, here, yeah. So in this case, as mentioned, so the stereochemistry up, and this should be the bond should be the down. So any doubt why regarding the stereochemistry that I have mentioned here? So if you don't have a doubt, so I hope you got the answers for these questions now. So if you just so these are the possible products. If you do the base created these startings with the base. Now just uh, identify the correct answer for this one. So you will get the correct answer among this. So therefore the option A is the correct option. So got the answer.
Yes, got the answer.
Yeah. So this reaction generally works in the SN2 fashion. So and also that's in the SN2 the backside attack takes place. In this case, what happened? So both this directing group attack in the same plane of this OTS. So therefore, this bond, if you look at here in the product, so this bond is in plane. So this is, although it doesn't look anti opposite to each other like backside attack, but if you look at planarity, so this bond is in plane. So attack takes place in the form of in attacks on this carbon in the same plane as this OTS group is there. So therefore, this bond looks in the plane. So that's what in our product. So option A, therefore, it is the correct option. But in case of the option C and D, sorry, in the fourth and third and fourth these two products, so this and this product, so what I have did, the attack same I did opposite side of this OTS. So in this case OTS directing upward, so attack of this hydroxy group takes place from the back side, that is from the downward side. In this fourth option also, if you look at here, so attack takes place here, uh, this OTS is directing downward, therefore attacks of this hydroxy group takes place uh, from this beta side, not from the alpha side, right? So therefore, I write this O directing upward. So I hope you got answer for this one now. Let's move to the next question. So this is the another question. I'll just zoom here also. Right. So I hope it is clear, visible on your screen right now. So in this question, what happened? The major product form in the following reaction. So if you look at the starting materials, what we have the epoxide. This is O, SBT, some protection here. And here we have the butyl lithium base, HC, triple bond C, TMS. So if you look at here, it has the some acidic proton. So in presence of butyl lithium, which is a base, so it will be act as a C triple bond, C, TMS, right? The C negative. in presence of base, that is butyl lithium. So this is what nucleophile we have. And if you look at how the nucleophile attack, so it can clearly see, you can see here. So this negatively charged attack from the attack on this position. So it will be go up. So this is what product we get. Now think of the stereochemistry at this chiral center, right? Now, so this is this chiral center is remain unaffected. So in the product also it should be unaffected. So if I just assign the stereochemistry at this chiral center, if you can help me in the assigning stereochemistry, it will be it will be good. So if you look at here, this will be one. So this will be the two, and this will be three, and this is the four, right? So if you just give the numbering one, two, three, this is the S. Sorry, S changes to R. Then in the product, if I just give the numbering to all, then you can see here one. Okay, now here the numbering change one, two, three, and the fourth. These four private directing downwards. So this will be one, two, three, S, two, three. But here it will be one, two, and three. Should be here it is yes. Okay. What are the other options that we have here? This is another option. So in which you can see here the one, this is two, three, and the fourth. And if I just give the numbering, so it will be one, two, three. It is again S, which is changes to R. So what is the answer they have given? Answer they have given here is the option A. But if you look at the Carl Center, the option it should not be the correct one. So okay, it's difficult to assignment between this whether this one is correct or this one. Mainly because if you look at the Carl Center, the accurate are we missing anything in assigning the stereochemistry for this two molecule? The option between A and B will be the correct one. Only thing, the configuration in the starting, it should be preserved in the product, and that one will be the product. So if I'm missing something in giving this RNS nomenclature, then it will be difficult. But if I just give the numbering here, the numbering should be correct, like this one, two, and three, and the methyl glucose. So it should be, so in this one, it should be the it is S configuration. But what about in the starting? In the starting, we have the oxygen get the first priority, then the CH2S, this will get the second priority, and this will get the third priority, and the methyl get the fourth priority. And if I just so it seems it's So if you just proper, you need to assign the stereochemistry. At this moment, I'm finding difficulty in assigning this actual stereochemistry.
Okay, then leave it and go for another one.
Yeah. So if you, I think for this one, uh, we cannot directly straightforward do S convert directly straight convert to the R. Mainly because of the orientation that we generally look for. Uh, so if you just we ignoring the that just by keeping this methyl group direct away from your site. So if you just look at from this site, so you don't really need to do the inversion in stereochemistry. So it should be at that moment. Just keep this CH3 group away from your site. So visualize it from the uh, this side. So what you can see, so this is the on the front face, that is the on the left hand side. This is on the left hand side. This is on the right hand side, and this is directing downward. Sorry, this is on the uh, lower part, right, between this left and right, because it is in plane. So at the time it you can see it is yes. So the configuration for starting is yes configuration. Therefore, starting option A, it also has the S configuration. If you look from this side, so you can clearly see one, two, and the three. So this is also yes configuration. So that yes configuration is maintained in the product as in the starting. Only if you just copy this structure and put on the camera, you can get the configuration for this one. So you can then only you can get the sorry. Then you can identify why the yes it has the yes configuration, not the R. So the actual configuration for the starting is yes configuration. Sorry, I just made the mistake. So the starting configuration for this car center is yes configuration, and therefore, if you look at product, it also has the yes configuration. So the configuration of product is also yes. So therefore, answer A is the correct answer. And if you look at the option B, it has the one, two, three. Again, this methyl group directing upward. So it has the R configuration. So option in this case, option A is the correct option. They are correct. So just uh, check how to assign the configuration in such system when we have sorry in this particular example when we have such type of orientations are given. So the assignment correct answer correct configuration is yes for this one. Why it is correct one that I'm talking? Why it is has yes configuration, not the R? So you have to figure out that one. But anyway, so it has the S configuration in the starting, so therefore you get the product also with the S configuration. Let's move to the next question. So we have here the sodium hydride treated with this alcohol. So what happened in presence of the sodium hydride? So it will be O negative, right? Now, if you look closely at this silicon SiMe3, so this is the example of E2 elimination reaction. So what happened in this type of elimination reaction? So if we have this type of group, so I'll just try to give simplified example first. O negative, and this is so SiMe3. So they form such a type of intermediate, and later it will directly convert this bond here, and this bond goes here. So it will gives the such double bond. The condition here is the the bond between carbon silicon and this carbon hydrogen, it has to come syn to each other. It should need to orient this one in the syn orientation, right? So if you do the syn orientation of this one, so what happen? What we get? We can get. So we need to rotate this molecule across this bond. So to get this in this in conformation. So if you just rotate this one, I will just delete the unnecessary content from here. If I just rotate this one, then what we get? We get like this. So now this Si, Me3, this R1, they are okay here. Now if you just do the rotation, So what we have did, we have taken this here, this here, and the hydrogen directing downward, which I have taken, sorry, which directing upward, which I have taken directing downward. So this hydrogen will be here, oxygen will be like this, OH, sorry, O negative it will be, and then this R2 will be here. So have you understand this one how I did rotation? So basically, if I just show it with the this type of orientation, so particularly, so when we have, let's say, take this example. So this is directing beta, this is directing beta. So this is directing uh, alpha, directing alpha, and we have this A, B, C group here, and here D, here E, and this is F group. Okay. So if you do the bond rotation of this one, let's say like this manner. So what happens? This A comes in the position of the B comes in the position of C, and C comes in the position of A, right? If you do the bond rotation like this, then what happen? What we get here? We get, so this will remain unaffected. So this D, this E was on the this side, and F was directing downwards like this. Since we did the bond rotation here after bond rotation, so C come in the place of A here. The A comes on the place of B, and the B came on the place of C. Sorry, yeah. Oh, sorry, I just given numbering incorrect. So this A comes here, B comes here, and the C comes here, right? That's what we did in this example also. And then if you try to do the elimination here now, so what we can get here, this bond goes here, and this bond goes to silicon. So what we get? We get a this double bond, this R2, this R1, and the remaining hydrogens, they will be as usual. So this is what product we get. So we get the option B is the right option. So uh, we have rotate the bond so as both this oxygen and silicon come in the one plane. Then and then only this intermediate step that's possible, right? Like this, and then elimination occurs. So that's what we did here. Therefore, option A is the correct option. And if you have any doubt regarding why not the epoxide and all, so generally in place of O, it will become O negative. But this is not that much good living group. In case of if you have look at the example earlier OTS, so if there was O tosylate, in that case I can say this can be from epoxide. But in this case, it's not gonna happen. So I hope you got the answer now in this question. So let's move to another question. So this 10th one. So if you look at the mechanism, sorry, the this look at this example, we have the aqueous H2SO4. And in this case, what happened? So when we add aqueous H2SO4, this hydroxy group get protonated. So when we have such group here, OH in place of H2SO4, so it will be converted into the, so I'll just draw the three bonds, all the bonds. Uh, it will be converted into the OH2 plus, because H2 is a very strong acid, like this. And this further converted into the, like this. So this is basically example of E1 elimination. So got the difference here. So this is the E1 elimination. Earlier it was E2 elimination. In this E1 elimination, once this intermediate is formed, then the last step is the, so is this intermediate form. So the bond pair between now here I will explain directly. So we have here the Si Me3, and we have the cation at this position. So it will directly goes here, and we get the product. So H2, it will directly in this fashion, you can directly draw simply and we get the as it is product A. Earlier, we need to have we need to compulsion to have the form this transition state. Then and only the reaction gonna proceed further. But in this case, there is no such what you can say. There is no such transition state required. Therefore, the stable one, that is the generally this type of E product is formed. It is very similar as one of the example that I have shown earlier also. So that's I think regarding the when we have such systems, let's say R1 and the R2, and if you do the H2 PDC reduction, sorry, PD already on carbon and the H2, sorry, H2 gas. So in that time, generally this type of syn olefin formation takes place. But when we add uh, the any metal such as the sodium or lithium in NH3, so this they provide the electron to this carbon, and so this reaction goes via radical mechanism, and in that case we get the stable olefin as a product. Sorry, because intermediate form, so we get here radical and this one forms here anion, and that's the in between step which helps to generally form this E product as a major product. In this case, the Z product as a major product. Okay, let's move to the further question. We have the another question, which is the predict the absolute configuration for the final product. So if you look at the, this is the S-glutamic acid, what we did, HNO3. So if you just let me know what is the role of HNO3 with this type of system, we have the acid functional group, we have this again another acid functional group, we have N2 functional group. What happen on which reaction center this HNO2 react? Anyone? So it is basically form N2, right? Something like this. Then what we have here, we have the acid group here. So this is like N2 is like now good living group. And so if you look at here, so this acid still have some electron donating this oxygen from of this acid still have some electron donating ability. So this attacks at this position and this N2 group eliminated. So what we get here? So we get basically this product. Now what about the stereochemistry? Okay, so the N2, this eliminate N2, whether this N2 is eliminated in the SN2 fashion or sorry, or SN1 fashion. So that we need to figure out. We have the COOH here and obviously hydrogen. So the options here given predict the absolute compression of the final product. So whether it is R, whether it is yes, or it will be racemic. Anyone? So basically, what happened? This has the lone pair. So it attacks on the backside of this N2 and N2 elimination takes place. Right. So what we get? The backside attack need to takes place on this one. So since this O in the same plane, so if you just do attack, and here I will just write down straight for the N2. So the compression, if you look at in the starting, what was the compression at this chiral center? It was this the one, this carbon get the second, this one get the third. So 1, 2, 3, it has the S configuration, right? So in this case also, if you do the attack on this position and N2 eliminates, so what will be the configuration and at this chiral center?
Actually, this in this diageochemistry maximum, I saw this is going by N2 gas evolution. That means carbocation is forming first. Direct, I did not see direct attack and nitrogen and leaving. First, nitrogen gas is going out, then it carbocation is generating, then OH is attacking. That's why I've given it. It will be racemic, but I my god, answer is
Uh,
wrong.
to form, as you mentioned, to form the recipe, first we need to form carbocation, right? As you mentioned. So, but if you look at the locality of this carbocation, where it is going to form COOH here, and now you can observe. What do you see at the carbocation at the alpha position to this carbonyl group? Is
Hmm.
it feasible?
Yeah, if I thought the COOH group is there, then it will be go with the SN2 type reaction, na? Then R.
Exactly.
But why it is S only? I think they have given S or something. Answer B answer
Yes.
is given.
Yes.
Either R or
Option.
it will be racemic. Both will. But how S is coming back again? Starting with S, coming back with S. So answer is really
Exactly.
confusing.
Exactly. So in this case, because since the chiral center here, this NH2 have the first priority in the product also, this will get the first priority. So it's not the issue with the shuffling of the what we call priority. Then that's the my concern. It should be the R, because we are not going to change the priority order also. So any initially it was nitrogen has the first priority. Now it has the oxygen has the first priority, which is the oncoming nucleophile. So it should have the 1, 2, 3. Yes, it should have the R configuration in my understanding. But why they have given this S configuration? That's the worried actually. In their exam, they have given the S, but I think the R is the more feasible, and I think R is the more logical answer here. Because if you look at the, as you also point out, so this is not going to form because it is alpha position to carbonyl, and carbocation at alpha position to the carbonyl is very likely to doesn't gonna form. So that's not the gonna happen here. So therefore, the SN2 fashion attacks takes place, SN2 attack, and we get the inversion in the stereochemistry here. So therefore, I think the yes option, sorry, the R option is the more correct option here. So anyway, I think the option they have given is, for me, it doesn't seem it's correct. So you can also have a look at this problem. So if you got the answer, please let me know. But if you go mechanism wise, the option A is the correct option as of, I mean, whatever that we have discussed up based on this one. Option A is the correct option. That is the R option, not the S. So anyway, you can have a look at this one, but I don't trust the answer that given in the assignment, the option B. Option A should be the correct one. Let's move to the next question. You can try to find out the why they have given this one, or maybe they have just given some incorrect options. Anyway, so let's move to the another further question. Predict the stereochemistry of the final product. Here we have added LiHMDS, which is the base. So, and then we have the PHCH2Br. So the LiHMDS, obviously it will abstract the proton here. So it will be O negative. The first one, because this is the most acidic proton. Now we have the added PHCH2Br. Okay. Again, so why they haven't did attack on this question? Still, again here also the one confusing. Because if you look at the proton here, it is this OH proton is generally more acidic than these protons. So 20 minutes more. Yeah. Okay. So if you look at here, this OH also you can also have a look. So this OH proton will be the more acidic. So the first equivalent of LiHMD is obviously gonna abstract this proton, right? So it will be O negative, and then the second can abstract at this position. It will be the C negative then. So I will directly draw here uh, this C negative here. Now the question about the how this nucleophilic, that is the benzene, gonna attack. So I don't understand how they have why they haven't did OBN protection or OBN formation here, but it should be OBN also gonna form in the product. Have you understand this? Why I'm saying this one?
Yeah, I understand.
Yeah. So anyway, the question is about the stereochemistry. What is the stereochemistry of this product? So forget about the how the reaction works and all. So we need to just find out, just focused on the stereochemistry of this product. It's just about the numbering. So you just give the numbering so you can get the stereochemistry. So if you just give the numbering, this C is should CH2, CH2, pH. So it will easy for you to give the numbering now. So if I just give the numbering at these chiral centers, what will get the first priority? Obviously, this group, this entire group will get the first priority. Second priority goes to this carbon which has this carbonyl group and hydroxyl group is attached. So this is the second priority. And third priority goes to this one. So if I just give the numbering, so how it will be looks like now. So the first, second, third. So this is yes, right? In the same manner, give the numbering to the another carbonyl another group. So that is here another chiral center. This will get the first. This will get the second, and this is the one third. So the first, second, and the third. Sorry, in the first one that did I did any mistake in the giving numbering? So sorry, first, second, third. Yes, it should change it to R because the fourth priority group is on the top side, right? So the it should be S changes to R. First should be the R, and the second should be the 1, 2, and obviously this is 3. This is S. So if I just label there, so it has the stereochemistry yes, and it has the stereochemistry R. So now think about the which is second carbon, second and which is third carbon. Because here it is also important. On which carbon you should say this is second and this is third, or this is second, this is third. That's also here important. So both are esters. So numbering, you can go from this side also. If this part is common, this part also common. Then the second part, if you go look at here, this is the oxygen. So we have to give the numbering. If you just remember IUPAC nomenclature, so how the numbering for this one looks like now. So this is the first carbon, the second, this is third, this is the fourth carbon. Am I right? So it should be 2s and 3r. Any doubt in this one?
No, I think it's okay now. I don't know what I done. I forgot.
So just let me check. Okay, in the product they have given answer A. Still again confusing. Whether I forgot the IUPAC nomenclature or what, I don't know. Can you also have a look at this
No,
one?
no, we are right. We are right. I
So
don't know. Probably during choosing option, they have done wrong or something happened. I don't know. But it is
yeah,
okay.
yeah, right. The longest chain we have to select. Then we have go by priority wise. So I think from this direction, if you go here, so up to this group is common. From this side also this group is common. Then what about the uh, next carbon? So next carbon has the CH2 group attached. In this position, the next carbon has the oxygen group attached. So we have to give the priority in this fashion: the first, second, third, and the fourth. So therefore I'm saying so this carbon is the second carbon uh, which has the hydroxyl group attached. So this is the second carbon and this is the third carbon. Therefore I'm saying 2s and 3r. Anyway, that's just common question about the stereochemistry, but just have refreshed the just regarding the how the assignment and is gonna done. But yeah, if you just look at the chiral center, they have the this stereochemistry. This chiral center has the stereochemistry, and this chiral center has the R stereochemistry. Okay, we'll take the next question. So I think yeah, these are about. I think this is the one question. Another one question remain. Okay, if you look at here, so the following transformation is example of whether it is diastereoselective, desymmetrization, enantioselective, desymmetrization, or esterification reaction, or none. So what is this? The option they have given, the option B. So that is the enantioselective desymmetrization. So what? So in this reaction, what happened? We have only one chiral center. So forget about the enantioselective anything. Sorry, forget about the diastereoselective, not enantioselective. Because if you have only one chiral center, at that time it should be about inertial selectivity. When we have more than one chiral center, then it will be concepts of diastereoselectivity. But in this case, we have only one selective chiral center. All group have the two equivalent. So it is all about the okay. Here also there is one another changes. This is the ester. Here it get the acid. So basically this is about more about inertial selective. Therefore, they have mentioned the inertial selective. But why they have mentioned this desymmetrization? Okay, they we have the very similar functional group on both sides. If you just elaborate the structure here. So we have this OH and CH3. This is again the same structure actually. on the both side. Sorry, not so OME. Okay, now I understand because I just got confused with this COME. So basically, these are the both are similar sides functional group, right? So therefore, it is selective desymmetrization. So nothing, anything here. So okay, these are the some problems based on the some assignment from the course. Okay, so in this course you have seen this is all the questions are mainly all based on I think stereochemistry. So we have seen some examples of the asymmetric. So hope you have solved this one. So this I think one more last question I think that I forgot. Okay, I will take that one also. For the synthesis of the following molecule, the retro shows will disconnect the molecule. Okay, so here in two heterochiral halves or into two homochiral halves. So what do you think here? So if you look at here, the if you just directly assign the stereochemistry or both of these points, you can clearly see both have the same chirality. So basically, we have divided into the homochiral compounds. Can I? Do you want to show me the stereochemistry here? So one, uh, this will be the second and third. So this will be the uh, so it will be S configuration. In this case also, you can see one, two, three. This R changes to S because this fourth priority group directing upward. So both are yes. So this is basically we have converted this into the two homochiral halves. And also, if you look at here, it has the C2 symmetry. So that's also one valid point. So option B is the correct option. So I don't think you should have any doubt in this one. So if in this case, let's just take the similar example, pH, and let's say here also the pH, and this is OH and OH. And if I did the disconnection at this point, so this will be into the two heterochiral halves. So because it has the configuration, which is so this is pH, right? So if you look at the configuration, it has the S configuration and it has the configuration 1, 2, 3. It has the R configuration. So basically, this is the example of heterochiral, and this is the example they given in the question, which is for the homochiral. So therefore, option B is the correct option. Okay, let's move to the one of the example that I have taken purposefully to show you. So this is very recent paper from the NCL Pune. So on the total synthesis of sorry, triplenone F. So if you look at the molecule, I will just zoom out the molecule actually. So it will be easy for your understanding. So if you come in the research field in the total synthesis particularly, you may come across such type of you may need to done such type of work. So here this is the one triplopenone F target molecule. And if I just show you how the reductions of this molecule is done and how we can initially think of different fragments from this one. So this is very good example that I think it's at this point it is you should able to know, right? So here so you can see. So this is molecule. If you just observe the molecule, how they have did the retosynthesis and how they cleave this molecule into simple smaller part. If you just go from the right hand side to the left hand side, you can see here. So the first cleavage they have did here is about. So here they have did the cleavage. How we can stitch these two fragments, the one fragment which is on the left side and the other fragment on the right side, how they can stitch together. So if you make them across one metathesis reaction, the Grubbs metathesis. So this is the classical example of Grubb metathesis. We can attach actually. So if we have this type of olefin, we can this R2, this R1. So we can add these together. We can get basically get this RCH2 double bond CH2 R. If I just give the color coding, that will be very easy for your understanding. So if you have these two R2, so you can basically get this type of new bond formation. And so if I just give, so this is the new bond is formed between these two molecules. So basically, the CH2 and this CH2 get eliminated, and this part entirely and this part from another molecule get attached together. So this type of reaction we call it as a metathesis reaction or the cross metathesis reaction. And if you look at the name reaction for this one, so this is Grubbs metathesis reaction. If you just Google it, then you will get to know. So I haven't really discussed regarding the Grubbs metathesis, but you can search about that one. So this is here they have did the bond cleavage, and we can couple this fragment together from the Grubbs metathesis. Okay, so that's why you can do here. The next fragment, so this is about the fragmentation or the cleavage of this bond, the first cleavage. If you look at the B cleavage, so this entire fragment, so on the left hand side, we can stitch together, attach to this group. It can be carbonyl. We can attach on this position by the Grignard reaction. I hope you understand the Grignard reaction now. So Grignard reaction, we have the ketone. We can add the Grignard R MgBr. So this, let's say R2 MgBr. So this R2 attacks here, and this molecule get converted into the corresponding alcohol. So that's what here did. So here bond cleavage. So this can be achieved from this one Grignard reaction. So this is the second B uh, fragmentation we can do. Then also we can the next fragmentation we can do here. So this one we can achieve by, if you look at here, how you can achieve this one. So this is the one some different example. So you may haven't really seen regarding this cleavage, but ignore this one as of now because this is some advanced some example which you may need to know what is this different type of reaction. We'll look some simple examples. Then we have here. So this is basically the uh, reduction followed by coupling cyclization of this part. So this part, entire part is comes from this COMe. So if you have the oxygen here, oxygen can attack on this ester basically, and it can get cyclized into the another ester. So this is type of ester. So if I just show you the how they have achieved the synthesis, so I can open out the paper actually. Okay, so this is the one paper they have recently published, and you can see here in the paper. So these are the different type of different fragmentation they have did, as I have also mentioned, and these are actually this type of basic cores as this tropulin molecule present in different type of tropulins, either tropulin A, B, C, D, and these tropulins are some, I think they are some biological active molecules. We are not gonna go into much more detail, but if you look at the how they have did here, so they have started their synthesis with the melanic acid. Melanic acid in three step, it converted into the this part. So this acid they have converted into the corresponding aldehyde, reduced to the aldehyde, and another part also they have did converted into alcohol, and then they have did the protection. So these are some three steps involved. And then on this particular, so this is the Grignard reagent. So Grignard addition of this on this type of protected compound. So basically, Grignard selective show addition on the aldehyde. So what they get? Uh, so this entirely group they got from this compound. So Grignard, and the second step was the PPST DIAD and 4-nitrobenzene. So that's the Mitsunobu reaction. So in the Mitsunobu, what they have did, the nucleophile here is the solvent is methanol. Okay, from this one, they initially got this one, and from this they have got this compound by Mitsunobu reaction. Inversion in the chiral center they have did here. Then there is further more reactions. So particularly the first one is the PMB, Br and the sodium hydride at the DMF solvent 0 degree Celsius. They got some intermediate, and basically the PMB protection are at this this position. And also they did the deproduction of such 1 2 diol using the acetic acid. So this is what they have did. Then later each involved. So DDQ and this DDQ and in the DCM. So basically this how the reaction mechanism goes from this one to this one, I'm also not sure because this is like not very trivial. So, but this is how we need to do the retrosynthesis and the synthesis of the molecule. So initially, if you look at here, so they have tried to divide this molecule into simple fragment, and they later they tried to do the synthesis. They did this intermediate synthesis followed by several other steps. So in this case also you can see this TMSCL they have added. So basically this TMSCL attack, if you add the one equivalent, then obviously it will form the OTS. Then the attack of this OTS, it will form the epoxide. So I think here the primary OTS formation takes place. OTS at this primary alcohol takes place, and then attack on this of the hydroxy. So OTS elimination, so epoxide formation. So these are the some small steps need to do doing the retrosynthesis. If you look at the other steps also, so what we have in this case, particularly from this step to this step, so this is like a Grignard reagent they have added. And the similar manner, one example that we have seen. So in this case, Grignard add on this aldehyde. So it will form this, and further it formed the intermediate alcohol, and then they did the this hydroxyl protection with the TBS. So that's the TBS protection they have did. So the two steps in have represented here. So first step is the Grignard addition across this aldehyde, and the same second step. So it will form the hydroxide. This hydroxide they have protected with this protecting group. Then if you look at here, so they have coupled this compound 3 and the 4 together. So basically this is the terminal alkyne. It has this acid proton. So this acid proton they have added to this. Once this acid proton is abstracted by this butyl lithium, what will form? It will form this C negative. Once it form this C negative, what it will do? It will attack on this epoxide on the terminal position. It will open OH. So that's what here did. You can clearly see. So this entire parts come from this fourth intermediate four, and this part, the one I'll represent here with the green. So this entire part come from the compound 3. So this is how they have did the synthesis. Then next also, these are the simple, small steps they have did. Some involve some complicated reaction mechanism, some are very simple. And finally, you can see here how many steps are required to get this enantiomer synthesis of this final molecule. So this is still intermediate actually. I think the final molecule is here. So this is still the intermediate to be. You can see here also there are several other steps, particularly again some additional group has attached here. So get this intermediate, then again they have used the Lindlar catalyst. Here is a clear example of the Lindlar catalyst that I have also mentioned several times. You can see here uh, this Lindlar catalyst, if you add on Lindlar catalyst, that is the H2PDC on the carbons and support on some barium sulfate or something. Can see the reduction of this bond takes place in the syn fashion. You can see clearly from here to here. So I have shown some theoretical examples, but you can see here the practical usage of this syn reduction. You can see we have the alkyne here. So alkyne converted into the syn fashion by using this H2PDC, right? So this is the one example you can get to know. So this is how if you work on the total synthesis, this rate of synthesis is very useful. And you can see finally they got the synthesis of this topo tricholinone. So that's the final molecule here. So, okay, these are some example. I will again show some simple synthesis which do not involve the chiral synthesis. I will show you some example from my research paper actually. Not from our group. I think I have one example here. I should show this to you. Okay. So this is the one recently published paper from our group, and you can see here. So this is basically on the some ESIPT molecule, that is the excited state internal proton transfer. So in that particularly the molecule in the excited state transfer the proton to their corresponding keto form, sorry, one tautomeric form. So that's the ESIPT stands for. Anyway, we are gonna look at the actual synthesis. Okay, here is the synthesis. So you can see, so these are the target molecule, how they have cleaved this molecule into different fragments. If I want to do the retrosynthesis of this molecule, what I will do, I can see here what are the different possible fragments. So what are the fragments? So we can attach this fragment to the so this is the one fragment I can consider. Here also this is the second fragment that I can consider. So this is how you can break this molecule into the simple fragment. Here also you can do another fragmentation. And if I just look at the synthesis, so you will understand. Oh, sorry. How the synthesis of this molecule done. So we have here this diketo compound. What we did, we have just simply treated this diketo compound with the uh, amine. So what happened? So the this amine and in presence of acetic acid. So first amine from the imine here, this PHOR, right? This imine formation takes place, and then we have this compound also in between. So this is the aldehyde. So I'm not sure what is the mechanism of this one, but in this case, when these two molecules reacted together and in presence of these aldehyde, it will form such intermediate and into the 30 to 25 to 30% yield. So depend upon the what the R group is here. So this is one starting metal, sorry, intermediate compound form. And then we just simply couple this with this boric acid fragment using from this position. So we get the target molecule. So if you just work on this mechanism of this one, I'm also not sure how the reaction mechanism works, but you can look at the retrosynthesis of this one. The similar manner, the another fragment can also attached. So if you look at the how we can select the different fragment based on our requirement. So if I want to attach the position at this position, I have taken this bromo compound. Now I want to attach the fragment on such positions. So I have selected this bromo compound. So depend upon our requirement, we can select the starting material that and we can make the synthesis of these materials. Further, one simple more one example that I will show. I think, yeah, this is the one another example. I'll just reshare this one. If you look at this simple synthesis, so here this acid converted to the corresponding ester. So how we can do the corresponding ester? We just added the methanol H2SO4. It will directly convert into corresponding ester, right? Then the next step is the addition of this R group. So this R group is endodecyl bicyclononane. So this basically you can consider it as a, alkyl compound anything. So this we can add basically borane, and the reagent here is the borobicyclo. This is basically boronic ester. So that boronic ester attached at this position by using this coupling reaction, and then this entire ester and this acid. So these are the two compound in presence of K2CO3. Oh, sorry. So this K2CO3 palladium DPPF is added for this coupling reaction because this is the boronate ester. So this is the 9-BBN. You may have heard about the boronic alkyl boronate. So that's the 9-BBN basically of these octyl chains. So the 9-BBN, that's we generally write in this fashion. So 9-BBN plus this bromo compound, bromo compound plus BBN. So basically, it's a kind of Suzuki coupling reaction they have did is using this palladium DPPF solvent. Then they got this compound. Then when treated this compound plus this acid together in presence of the lithium hydroxide methanol in THF at 65 degrees Celsius for 18 hours. So it will form this compound in which this R is equal to 9 dodecyl, and then here there is acyl chloride formation by using the SOCl2 and followed by so this is all one pot reaction from here to here. The SOCl2 added to it will convert into this acid to the corresponding acyl chloride, and then the indigo dye is added. So this indigo dye and this acyl chloride reflux in the xylene for 3 days, it will give the formation of this final molecule, only the 7 to 7%. So when we have this R is equal to dodecyl chain. So this is not very, dodecyl means the 10 carbon. So that chain if you have, it will, so this R is equal to this alkyl chains. Here also this alkyl chains. So only the 7% product formation takes place. So you can see the complexity of reaction, but we can basically do the synthesis in this manner. If you look at more similar, simple examples, so you can also have a look at the some very simple examples actually. Yeah, here. So this is one very simple straightforward synthesis. So this was our target molecule, which involve. So in central linker is the terfluorine. So this is the terfluorine linker, and we want to add this type of group on this terfluorine linker. So how we have achieved the synthesis of this molecule? So you can see we have the terfluorine. We just did the dibromination. So we get the dibromo terfluorine. So up to here is okay. Now how one can get this one? So to get this one, so initially we have the starting material. So this is the aldehyde. We have treated this aldehyde with the carbazole. So this fluoro, we have this aryl fluoride, and we treated with this carbazole. As once I have mentioned, so this is basically aromatic nucleophilic substitution reaction. Example of aromatic nucleophilic substitution reaction. So if you have the aryl fluoride, we can and when it treated with the carbazole, so this fluoride. So this end directly attach on this position and the fluoro get eliminated. So this is what the example of this aromatic nucleophilic substitution reaction, and we get this carbazole couple this compound. So this is aldehyde. And the second step is the what the second step? We have this PPH3CH3I. So this is Wittig reaction. So you know the Wittig reaction. So if you have the aldehyde and when you treat it with this, in this example CH3 PPH3, initially we need to add the base. So what will have? CH2 minus PPH3. Sorry, here it is plus PPH3 plus. So this is what Wittig salt we get from. And when this Wittig salt treated with this aldehyde, what will happen? So like this. So in this case also, if you can look at directly on the example, so this is what we have the Wittig salt. Wittig salt, the same Wittig as I shown here. Wittig salt plus aldehyde, it will form this bond, this olefin. So this intermediate two, when we couple with the dibromo fluorine, terfluorine here, this entire center part it was called as a fluorine. So when we treated with these olefin with the aryl bromide under Higg coupling reaction. So what is condition for Higg coupling? Palladium acetate, uh, PO tolulyl to basically this is the ligand. This is the palladium catalyst in place of the organic base triethylamine in DMF solvent under argon in absence of oxygen basically. At 90 degrees Celsius, it will give the formation of this BSTFCZ, that's the final target molecule. So this is how one can do the synthesis of these of the material. So it's all about our synthesis course. I hope I have tried to show give you a flavor about how the synthesis is works. So I will stop sharing here. So if you guys have any doubt, please let me know. The floor is open for any question answer. And also, if you have any doubt, general doubt regarding anything regarding how the IIT system work, how the research work, that also you can ask me. So,
Sir, which software are you using during a presentation? Means teaching us?
oh no, no, I just try directly simply you do on the PowerPoint.
No, no, no. You are writing na Chemdraw. It
Okay,
is not
okay.
Chemdraw.
Uh, for writing purpose, I directly use
And
the
drawing
this plain
structure, drawing structure.
drawing structure CameDraw. So do you want the free access to CameDraw? I will share the link. That's okay.
Okay,
For
okay.
trying this one or for trying CameDraw?
Okay,
What
okay.
for writing the structure?
All those writing the structure and actually it is
Okay.
what file you are doing the presentation.
Presentation directly I'm doing on the this presentation directly on this one. But writing I'm doing with the one of the sorry this we called it as a some Huion writing pad is there. So I have taken it from the Flipkart. You can use that one.
Okay, okay, okay.
But for
So this
writing,
is
okay.
purchase version.
Yeah, yeah.
Okay,
This is no, it's hard pencil and the pad type of system that I have
okay,
purchased. Yeah.
okay, okay.
And for writing the drawing the structure, yeah, I can provide some free accessible CamDraw. That one, sorry, what do you call CamDraw file
Okay,
software.
okay.
If you want CamDraw, then please let me know. I will share that one. You just this is my contact number. If you
Yeah,
have any doubt,
I'm already taken screenshot your contact number
so
and
I
mail
can
ID.
provide the free CamDraw. you can directly install. I have the what you call serial and anything whatever required. So for processing the NMR, I have the Mistro Nova.
Okay.
You don't really need any access key to take that one. And anything software, I don't think which is Origin is available. I think, but if you have the student account, you can access the Origin. But I'm not sure whether you can able to access that one. But Origin you can directly download from the software, and you can request the free access of the Origin from their Origin website. So you just need to answer a few questions there and need to
Hmm.
fill some small information. I don't think anything else required for them.
Okay. Thank
So
you.
you can get the Origin. Okay.
Thank you.
Anything else?
Ah,
So we are concluding our course. I hope when you guys have your quiz online examination. So I'm not sure about the date. So what's the date
this
for
is
the examination?
26. 26.
Okay. Okay, 26. So best of luck for you guys for your
Yeah, this
exam.
is computer based exam, but they will give some pen and paper because sometime we have to draw the structure also.
Yes, I recommend you guys to keep blank paper and pen with you
Acha.
because I'm not sure about the particular exam center, whether they provide you pen paper or not. But
Okay.
always be prepared. Keep blank A4 size paper, two, three papers with you, one pen, pencil, whatever you have with you.
Okay. Acha.
And I'm, I think you don't really in this course don't require any calculator or anything. So just keep the pen and paper with you. Just also refresh all the assignment questions that given on the portal. Mostly the question may come from the assignment and the whatever discussed by the professor. So that's about this course, I think.
Okay.
This is the
Okay.
last one, sir. There will be no.
Yes. Yeah, I think this is the last session. Professor has also taken, I think, the session last week. Something I don't think. I'm not sure whether you guys have joined that session or not. Mm.
NK, did you get the hall ticket?
Yeah, I got the hall ticket.
How? I am unable,
They are sending the link. Through the link you have to go.
but I have gone
I
through
think
the link.
you can check your register mail.
Yes, the link is shared on the registered mail ID. So ID.
Yeah,
So
yeah.
just have a look at
You
the
have to.
registered mail ID.
I think you got the mail because who have another person is there who had exam in 19 because he's from math background, so he also got a hall ticket. So I think you got him email. Please check it.
So keep noted my mail ID. If you have any doubt regarding anything, just send me the mail. I will try to answer you as early as possible. And if you need
Yeah,
any
already.
proofs,
I already have taken screenshot
yeah,
of your email ID, so
yeah.
I'll if I
So
need I'll contact you.
So best of luck you guys for your
Yeah,
examination. And
thank you so much.
I like to also mention you guys. So if you guys, I'm not sure if you guys are interested in doing training or anything or any internship. So you can directly ask professor for training or internship. Since you have taken their course, so you can directly send them mail after the examination. Sir, I want to apply. I want internship opportunity under your lab. So those who have completed the course under them, they have some privilege. So from the NPTEL side as well, NPTEL side also providing some fellowship for those who have completed the courses. So try to take advantage from that one. So you will get opportunity to work in various IIT, whichever you want, and under any professor, I think. So, okay, we'll stop here for today. And I think this is all about this course. So, thank you so much for joining and thank you so much for this taking the course on NPTEL.
Okay, thank you.
Thank you.